to the partial coefficient of materials. Every material has its own partial coefficient, and partial coefficient pi AB actually divided by when you apply the electrical circuit into this device composed of A and B, then how much heat you can absorb from surroundings or how much heat you can release to the surroundings. This we call the partial coefficient. So let's take a look how what's the partial effect and what's the device of partial what's a device for the partial effect. And this is the device composed of material A and B. And we extra put a power supply here inside this electrical circuit. And here we find interesting stuff. We find that when we connect to the power supply, which means we supply the electrical circuit through this device, and there are some heat J capital Q absorbed from surroundings at these junctions. And also we find that there's a set amount of heat flux J capital Q be released to the surroundings. So if you focus on this device, you will find that this actually is a prototype for the cooler, or some people call it as a heat pump. It absorbed the heat from one side and release the heat from outside to the outside. So like some air conditioner or the cooler. So you can cool your materials or cool your materials or your environments down at this side, and you deliver the JQ to the other side or the other environment. And I hope you can write down the N-type materials and label them here. Okay, so why actually the partial coefficient pi AB? AB means this device composed of A and B was defined as how much electrical circuit we apply through this device and how much heat this device can absorb from surroundings and or release to the surroundings. This we call the partial coefficient. And why I hope I ask you to label this A and B. It definitely belongs to N-type materials. Let me show you why. We put the battery here, so you know the direction of electrical circuit is this direction, right? And as you know, the N-type actually the carrier is electrons. So when we discuss the heat, always the carrier moves, then they always carry some heat on its own. So in the N-type materials, in material A, the electrons moving to upward, right? It's the upside direction with the electrical circuit. So the JQA will be like this way. And this is when we discuss the B materials. The B material, if it also N-type of materials, then we talk about the heat flux JQB. It definitely is upward. So if we look at these junctions, the reason we need to identify JQA and JQB is we want to know how to get the JQ, the heat, J capital Q. So we focus on these junctions. How much heat flow in should be equals to how much heat flow outside at this junction, right? So based on this, we know JQ equals to JQA minus JQB. The reason is, these two inside, the heat flow inside will be equals to JQA. So JQ plus JQB equals to JQA. So when you want to know the value for JQ, you can use the JQA minus JQB. So this is a Peltier coefficient. Now you know that, right? Okay, so next, I'm going to demonstrate how we get what's the relationship between the Peltier coefficient and also the coupling coefficient, okay, or in this Peltier effect. So first of all, we write down there's two possible driving force. For sure, there's an electrical current. We put the power supply, so definitely there's a electrical potential, right? So you got the current density, and because we absorbed some heat and release heat, so maybe there's some, probably, I will use the term probably, the heat flux do something. So I also write down the heat flux term, direct driven by F capital Q and coupling indirect driven by F small q. Then you substitute the F capital Q and small q with this term. And next, there will be a very important stuff or assumption. This device actually is performed on a constant T, which implies that there's no temperature gradient along these materials. Actually, this is the same idea what you observe we mentioned that in Seebeck effect. But anyway, we assume there's the device, there's not a temperature distribution, temperature variation along material A and B. So we will say constant T. Based on constant T, you can directly delete the thermal F capital Q, delete the dq T over dx. So what you have is you have this term and this term, right? And based on this, we can express the heat flux in terms of current, electrical current, by this coupling divided by direct coefficient. And when we focus now, you know the J capital Q, right? J capital Q. So we try to emphasize J capital QA and J capital QB. So as you know, A material, B material has its own coupling coefficient, but they have the same electrical circuit passing through, right? So JQA minus JQB, we mark, label these terms belongs to A material minus this term belongs to B material, and they have the same electrical circuit. And in order to know, the Peltier coefficient is the J capital Q, which is JQA minus JQB, this term, right? Minus or divided by electrical current. So this term divided by JQ. So we got this term minus this term. And what's this term? If you check the previous line, coupling coefficient divided by L small q actually is ST, Seebeck coefficient times absolute temperature. But however, there's something difference between, right? This one is small q capital Q, but however, the one we just mentioned is capital Q small q. So based on Ansaka symmetry, this symmetry principle actually tell you the L capital Q small q equals to L small q capital Q. Based on this, we can write down the Peltier coefficient equals to SAB times T. So we successfully to link the Peltier coefficient with the coupling and direct coefficient term, and also highly related with the Seebeck coefficient. And this is a pair, right? This means the pi AB or SAB means the pair. the pair of material A and B. But as I mentioned, every material has its own partial coefficient. The weight also is J capital Q divided by JQ. So you also get the coupling coefficient divided by L small q equals to ST. Okay, so here probably you may have two questions. The first one would be, Professor, as you mentioned, every material has its own partial coefficient, even seebeck coefficient and seebeck coefficient. Why? The example you show here, no matter is the power generator, thermocouple, or this cooler, these examples, we find that actually they are a pair of material. That means the composed of A material and B material. Why? The answer here would be because the reason is when this means implying that the partial coefficient is very small. That means when I apply the electrical current, but the heat J capital Q is too small to used for applications, no matter it's a cooler or a power generator. So that's the reason why we need to use two or more pairs of this material to be a generator or a cooler, because the efficiency of a single thermoelectric material is very, very low. Okay? And the second question some people ask me is, or want to, I need to emphasize is, for this cooler, for this the partial coefficient for this AB, this cooler, if based on this equation, do you have any idea to increase the efficiency of this cooler? The answer to this is increase the efficiency. That means, what that means? It means that when I apply the same electrical circuit, I hope I can get the maxima or value of JQ, right? But in this case, JQ equals to JQA minus JQB. This definitely are not the maxima value, right? So how we can increase the efficiency of this partial coefficient of this device would be if I can allow the JQ equals to JQA plus JQB. In that case, the heat flux JQB, the direction should be go this way, should be downward, right? In that case, the downward means the JQB, the direction of JQB is the same direction with electrical circuit. That means the better way to reach the maxima cooler by this thermoelectrical materials would be, use the P type here. Sorry, it's a little bit ugly, the writing, right? So in order to increase or reach the maximum efficiency of the cooler made by thermoelectrical material or made by the partial effect, NN is not a good idea, but NP will be can reach the maximum efficiency of A and show you in our PPT slide is the when A and B materials belongs to N type, right? And the partial coefficient is expressed like this, JQA minus JQB. And as I mentioned, if you change material A or material B as a p-type material, then the difference way would be the heat flux, the direction of heat flux JQB will be downward. So that will result the JQ equals to JQA plus JQBY, because at this junction, how much heat are absorbed from the surroundings would be equals to how much heat flow out of these junctions. So this value will be JQA plus JQB. Okay, so this value definitely larger than this one. So in this combination, it can reach the higher efficiency of this device. But how about, some people probably ask, how about PP? When material A and B belongs to p-type materials, then for the p-type materials, the carrier flows along the same direction with the electrical circuit. So JQA will be like this way and JQB will be like this way. So if you focus on these junctions, you will get this JQA plus JQ will be equals to JQB. So when you ask about the JQ, it will be JQB minus JQA. So this efficiency and this efficiency definitely smaller than this efficiency. So this is just for your reference. Okay, so let's back to this slide. So I also grabbed these figures from the internet, and what this figures means actually is an N-type and versus the P-type particular element, means the materials. We have N-type material when I apply a circuit, electrical circuit, and but in this case, actually, the electrical circuit is going this way, and the electrons definitely flow in the opposite direction, with the electrical circuit will go upward. In this case, the electrons will carry the heat from this side toward to this side. So that's the reason why we can cool this side down, because the electrons carry the heat from this side to this side. So we can cool this substance or environments down. So let's take the other N-type material as an example. We also apply the electrical circuit in these directions, and the carrier is hose. Hose flow in the same direction with the electrical circuit. And as you know, the carrier carries the heat, right? So the carrier carries the heat from this side to moving toward to this side. So this can cool this side down, because more or less the carriers always carry the heat from this side to move to this side. Cool this side down and heat this side up. The same idea. So the particular elements create an upside temperature gradient. Okay, based on different types of materials. The reason is the different types of carrier, right? Okay, so give you a summary here. Particular coefficient, actually pi AB is related with a coupling the coefficient divided by direct coefficient, and also proportion to the seebeck coefficient. If you want to measure it correctly, you need to perform under the isothermal conditions, means the dT over dx temperature gradient equals to 0. There's no temperature gradient along these materials. These are very important assumptions. And at the end of these lectures, I want to introduce the important Osaka symmetry principle. These are very important assumptions. When you describe these principles, we assume this is let a local equilibrium be reached, means the dq over v, the volume, equals to TdS. Okay, then this will be applied on irreversible process. Okay, irreversible. If reversible, ds equals to 0, right? So under this irreversible process at local equilibrium assumptions, which also we always use to describe the flow process in kinetics. We know the entropy production rate is larger or equals to 0, and we also get the flux-force relationship. And under these situations, what's the Ansaka symmetry principle, which is used to describe this coupling coefficient? There'll be a symmetric coupling coefficient, so means Lij equals to Lji. So let's think about what's the Lij. The definition of physical meaning for Lij is the changes in flux of entity I caused by the driving force J equals to the changes in flux of entity J driven by the driving force I. So in most of cases, we observe these results are correct in most of cases. So some people call it is not only assumptions, which we call a principle. So the deviation of this Ansaka symmetry is based on microscope reversibility for systems near equilibrium. Okay, so by using this Ansaka symmetry principle, in the beginning, when you write down if there's a two driving force, F capital Q and F small q coexist on this system, you will directly write down these two flux expressed like this way. And in the beginning, you got 1, 2, 3, 4, you got 4 coefficients, unknown coefficients, right? By using this symmetry, Ansaka symmetry principle, this term will be equals to this term. So now you only have 3 unknown parameters or coefficients. So this is the reason we want to emphasize this principle. This will help us to decrease the numbers of unknown coefficients. Okay, so let's move. Before we end these lectures, I'm going to give you an exercise. But here, I hope you can delete these terms for me on your handout. Okay, so what we have here is we have a material subject to temperature gradient and the electrical field. So there are two driving forces. And if it connects to another conductors by forming a closed circuit, please calculate the J capital Q, J small q, and also calculate the entropy production rate per balance in these systems. Okay? So I'm going to switch to the iPad to show you how to solve these questions.
And we subject to a temperature gradient of this value and also an electrical field. So what you have here is you have a material and there are two driving forces applied on it. One is the thermal driving force. The other one is the electrical field. I mean the driving force of the electrical field. So if we connected this materials to the other connector to forming a closed circuit, could you please help us to do what? Calculate the heat flux. Sorry. So can you help us to calculate heat flux and also the current density? And problem C is can you calculate what? The entropy production rate. Okay, so let's do this. First of all, we need to draw the pictures. We have materials here, and we connect it with electrical field. Okay, so we assume this is T1, this is T2, and this is phi 1, this is phi 2. So let us plot the temperature as a function of location here. So this is T. So we assume here T2 is higher than T1. T2 is high temperature gradient, right? Okay, so we assume T2 is larger than T1. And also plot the electrical field as function of location. So what's the relationship between the phi1 and phi2? We assume the phi2 also higher than phi1. Okay, so let me just draw this. Okay, so now we know, and as we know, the temperature gradient is this value, and the electrical field is 600 per meter. Okay, so the question is, the first one you need to calculate the heat flux, right? And now we have two driving forces, so you need to use the flux force equation to formulate heat flux, right? So heat flux can be expressed like what? Direct driven by thermal force and the drag coefficient plus there's the other driving force is electrical field, and also electrical field contribute on the heat flux. So you can use the same idea to get the current density. Current density is directly driven by the electrical field, and you got the drag coefficient, and current density over also contribute by the thermal driving force, and the coefficient is like this because the driving force contribute on the current density. So we just put all the information here. So what's the L capital Q capital Q? It's a kappa T, right? And what's the thermal driving force? Is minus temperature gradient divided by T. And what's the L capital Q small q? Is the low as T. And the driving force here is the electrical potential gradient. So here, drop this term out. So you get the thermal kappa is equals to 1. So you know kappa is equals to 1, right? Kappa is 1. Okay. And the temperature gradient minus temperature gradient. So here, the temperature gradient T1 minus T2 is positive because T1 higher than T2. And so T1 minus T2, or T2 minus T1 is a gradient, right? So it's a positive, and you have a minus here, so it's negative. So here it should be negative gradient times to 6 plus though electrical conductivity here, the information I give you is the electrical resistivity. So you need to convert this to electrical conductivity. So if you convert it to that, so it'll be the 10 to 5. Okay, and seabed coefficient is 200 micro. And the T here is average is 300. Okay, then you got the what is the minus electrical potential gradient? So phi2 minus phi1 is positive, then negative. So it's a negative. Okay, so you got, after simple calculation, got the minus 6.6 times. Okay, so you need to put the order, the unit here, right? Okay, so let's take a look on here. The value for heat flux is a negative. So negative means you need to check to the graph you just draw. So negative here means the flux is toward to the left-handed side. Yeah, so Okay, so it looks okay, right? Because so the heat flux is toward to left. So it just tell you the direction is to the left for the heat flux. Then let's move to the current density part. Current density part is what's the L? Small q is low, and electrical potential gradient minus, and also so it's low ST, and temperature gradient divided by T. Then you just took the T, then fill all the, what's the low is 10 to 5. And what's yes, the minus, the electrical potential gradient is minus 600. And rho is 10 to 5. Seebeck coefficient 200 micro. And the minus temperature gradient is 10 to 6. Okay, so the result here would be minus 1.2 times 10 to 8. And this is minus, so the direction also is to the left. So the finally current density direction is this way. So the C just asks you to calculate the entropy production rate, right? So be like this: flux, driving force, plus the flux, driving force. So got 300. So it's minus 10 to 6. What's the driving force here? Would be the minus 300 plus this one times minus 600. So the results will be around 4.6, 10 to 8. Write down the is 1. Okay, so this after calculation, then what you got here is this value is larger than 0. So this is you got the entropy production rate per Valen, and this value is larger than 0. Just tell you these reactions. The reaction means that when you have a thermoelectrical material and you apply a temperature and electrical potential on it, and the profile, the direction is showing that in both of this graph I just draw. So in this direction, that means the temperature gradient is the same with the electrical potential gradient at this situation. Then we after calculate, we can first of all we can confirm the direction of the heat flux, current density, the direction of heat flux, and also the direction of the current density is to the left-handed side, and actually the entropy production is larger than 0. That means tell you that after you apply this driving force, and the system can reach the steady flow process. It's a kinetics process, and it's an irreversible, spontaneous process. And some people probably ask, how about if I switch the direction of the battery? Switch the direction of the electrical field we apply on this system. Because actually in these questions, we didn't, this question didn't point out the direction related to what kind of direction of the electrical field you apply on this system. So how about we switch the direction? For example, it's like this. So in order to answer this kind of question, I will do the same thing, like T. So I will draw T2, T1, and the only different part will be what is the electrical potential part. So now the direction is like this way, it's phi2, it's phi1. So the gradient direction of temperature and the electrical potential are different and show like this. And I believe you also can simply just calculate the heat flux here. So the heat flux here is you can just copy that. It's 1 times. The only different part will be the will be what? Will be the minus electrical potential this term, right? So you can just simply copy the rest of it times 300. But the rest of it should be what? Because you switch the, sorry. So the direction should be positive, right? 600. Why is positive? Because phi1 minus 2, phi2. Phi1 minus phi2 is negative. And negative electrical potential gradient, negative becomes to positive. Okay, so the result here will be 6 times 10 to 5. And this is what? Positive. So the direction is go to the right-handed side. So in this case, the heat flux is go this way. Okay. And how about current? How about current? So current is the same, right? You can copy, but you need to pay attention. This will be positive 600. Then the rest of it just copy. Okay, and result will be equal to 0. So there's no current density because the effect, the current density driven by the thermal driving force and the electric field are the same but with different direction. So the results come out, there's no current density exists here. So for the entropy production rate, because there's no current density, so the entropy production rate here, you just need to consider one driving force, right? It's J capital Q F capital Q. So B, sorry, yeah. Six times 10 to 5 minus. So result would be around here. But interestingly, the entropy production rate is negative. So just show you what did this result tell you. When even you apply the because entropy production rate is negative, that tell you this is an impossible process, right? Impossible state of kinetics process. So even you apply this temperature gradient and connect this with the battery, but this system is not going to become a steady state flow process. So this not going to is a reaction. It's not. This is not a kinetics process because entropy production is smaller than 0. It's not going to happen. It's not going to happen to just show you that this reaction is not going to reach steady state flow process. Okay, so this result is interesting, and hope let's end it here, and hope you have some idea about how to get the heat flux current density when there's two driving forces coexist or co-apply on the system, and also hope you can use the entropy production rate to well describe your interesting flow process, and you can determine what kind of system, what kind of flow process is possible, and what kind of flow process is impossible. Okay, so by after serious calculation and by using the value or magnitude of entropy production rate per volume you calculate. Okay, so today let's end it here.